Welcome to video 6 in my series on quantum mechanics without maths. I've decided to repeat just a little bit of the last video, but with some slightly better graphics that aren't hand-drawn this time. The graphics are done using JavaScript, and you can download the web page here if you want to play around with them a little. In the last video we looked at the throw of a die and the likely position where it might fall on the table. The position tended to group near the centre of the table, and we got a probability distribution for the distance like the following. This is a typical bell-shaped distribution. The die is more likely to land in the middle of the board than it is at the ends. Because this is a continuous curve, we can apply the slope operator to it. The slope operator just measures the rate at which the curve is increasing or decreasing at each point. The slope at each point becomes the value of a new curve. So we take our wave function w and we apply the slope operator to it. Now we saw in video 3 that if you've got a wave function corresponding to a measurement, then measurement operators applied to it have the same relationship to one another as the underlying measurements themselves. That's why these wave functions are so special. When we apply a measurement operator to a measurement wave function, we expect to get the same wave function back multiplied by the measured value. So let's see if that works on our bell curve. You can see as the slope operator acts on each point of our bell curve, it traces out a new curve, the red curve. For example, where the slope is at its greatest, so is the value of the red curve. Where the slope is flat, the red curve has a value of 0. It's clear straight away that the new curve looks quite different from the bell curve. We don't get the same curve back when we apply the slope operator to a bell curve. What this tells us is that the bell curve doesn't represent a measurement wave function for the slope operator. This is going to be really important in a moment once we figure out what the slope operator actually measures. Now think about what happens as the die rolls and begins to slow down. Its location becomes more and more certain. The bell curve becomes narrower and narrower, and taller as the area under the probability distribution must remain 1. Eventually, the centre of the die is stationary at a fixed location on the board. Its position is certain, and the bell curve narrows to a single infinitely tall and thin line. Now, in reality, there's no such thing as an infinitely tall and thin line. It's a mathematical idealization, like a perfect circle or a geometrical point. They can never be realized in the physical world. Even in classical mechanics, we can't measure the position of a die with perfect precision. Classically, there's always some uncertainty in how well we can measure the position of the die. We'll see shortly that the same is true in quantum mechanics as well. We saw in the last video that exponential curves are measurement curves for the slope operator, but we rejected those as they grow too big. Next, we finally looked at waves. A wave is nearly a good measurement function. We'd like the slope operator to act on it and give us the same function back times a measurement value. But instead it gives us a wave function that's a quarter of a wavelength out. The solution is to have two curves in our wave function. The slope operator acts on the blue curve here in exactly the same way as on the previous slide. We're just looking at it from a different angle. However, now we add something extra. Remember in video 4 when we did the coloured die example. we had to introduce a new kind of number that we called I. I wasn't a positive or a negative number. Instead, it stuck out of the board. We think of it as a rotation as well as a number. We're going to use I again. This time we apply our slope operator to give us the red curve, but then we multiply the result by I. This rotates the entire curve. Now we apply the slope operator to the red curve itself. Then we multiply it by I as well. It rotates back to the same position as the original blue curve. So by applying I times the slope operator on both the red and blue curves, we simply cause them to swap position, giving us the same pair of curves back, times a measurement value that here we're calling P. This is exactly the behaviour that we wanted. So now we have a well-defined pair of curves that can act as a measurement function for the slope operator. But what exactly do we get when we take the slope of a pair of curves that square to form a probability distribution? It's not at all obvious. To answer this question, we need a mixture of theory, experiment, and inspired guesswork. In short, we need some physics. In 1900, Max Planck was trying to explain blackbody radiation. This is the spectrum of light emitted by a body in thermal equilibrium. Planck could only explain the spectrum if he included the assumption that light was exchanged with the body in packets. The energy contained in each packet, E, was proportional to the frequency of the light being emitted or absorbed, times a new universal constant h, now called Planck's constant. In 1905, Einstein used the same assumption to explain the photoelectric effect. Once again, light seemed to be behaving like a small packet of energy. In 1913, Niels Bohr was able to explain the observed spectrum of the hydrogen atom by assuming that the angular momentum of electrons comes in discrete packets. Louis de Broglie then speculated that if light waves could behave like particles of energy, maybe particles could behave like waves. It's fairly easy to derive a formula that relates a particle's momentum to its wavelength. This just comes directly from the original assumption of Planck and Einstein, plus a little bit of relativity. The assumption is a good fit with Bohr's model of the hydrogen atom. With this assumption in place, everything just works. The waves we've constructed on previous pages are almost the momentum states for a free particle. The value p that we get from our slope operator turns out to be the momentum of the particle. As this is a probabilistic theory, you find it's the average of these measured values that behaves like classical momentum. There are also theoretical reasons to associate the slope operator with momentum. I times the slope operator can be used to generate translations in space of curves. The conserved quantity associated with translations in space is momentum, so even in classical physics the two are related. Before we can reveal the full quantum mechanical momentum wave function, we just need to add time. We start off with our typical wavy wave function. To avoid clutter, I'm only showing one of the two curves that we saw previously. Now we set the curve moving. It doesn't just change values over distance now, it also moves with time. Now we pick a particular distance along the horizontal axis. It doesn't matter which point, any one will do. black dot moving up and down shows the way probability will vary at a particular location over time. So now we can plot the value of the dot over time. This is shown in the red curve. The horizontal axis for this curve is time rather than distance. It shows how probability is varying with time, and this is a wavy wave function as well. Since we have a continuous red graph, we can apply the slope function to it as well. But as the slope is being taken with respect to time rather than distance, we'll give it a different name. We'll call it T for time operator instead of S for slope operator. Just as with the slope curve, we want to find wave functions that will give us the same wave function back times a measurement value. And for exactly the same reasons as with the slope operator, we need to use a pair of curves and a time operator that is multiplied by I. And purely as a convenient convention, we stick a minus sign in front of it. This is purely to make positive measurements correspond to waves that travel in the positive distance direction. By a similar argument to before, a mixture of experiment, theory and educated guesses, we find that the thing we measure with this operator is the energy of a particle. We're almost ready to put together the wave function for a free particle in all its glory. First, let's return to our pair of measurement curves for the slope operator. We take the value of the blue curve, that's represented by this blue line here, and then we take the value of the red curve, that's represented by this red line here, and then we add them together. The probability is the square of the length of this grey line here, which is the sum of the red and the blue lines. We repeat this at every point along the distance axis, and we finally get this. We set it in motion to get the full wave function. I've coloured the radial lines to emphasise the angle that they make with the distance axis. Just to remind you what this is, it's the measurement curve for the slope operator multiplied by I. You square the length of the radial lines to get the probability of finding a particle at each point. Only the distance axis is actually a measurement in real space. The other two axes combine to form a probability distribution. From a mixture of experiment and theory, the wavelength defines the momentum of a particle. Shorter wavelength means bigger momentum. The frequency defines the energy. Higher frequency means higher energy. Basically, the faster that it moves round, the more energetic the particle is.